Hello and welcome to the validation of 5G-Ready OpenNebula Edge Node screencast. In this screencast, we are demonstrating the validation of 5G-Ready Edge nodes on OpenNebula using the Silva-compliant software stack. We will show how OpenNebula provides the carrier-grade enhanced platform awareness capabilities, also known as EPA, required for 5G workloads. The 5G workloads, such as vRAN and UPF, require specific hardware capabilities like SR-IOV, BTP, and CPU pinning, something that standard cloud provisioning often tend to ignore. Our solution is a Silva-compliant stack using OpenNebula as the infrastructure provider to automate the zero-touch provisioning of these specialized nodes. To prove the works, our strategy is to validate the node's readiness by deploying a carrier-grade CNF, the 6-wind virtual service router that explicitly demands these capabilities. Let's look at the stack from the bottom to up. At the infrastructure layer, OpenNebula manages the virtual infrastructure, enabling hardware acceleration via the SR-IOV HugePages and the CPU pinning. At the platform layer, we have two Kubernetes clusters, the far edge cluster representing a remote cell site and the regional core cluster representing a security gateway. At the network function layer, we will run the 6-wind instances, including a virtual cell site router at the edge side and a virtual security gateway at the core location. Why 6-wind? The 6-wind virtual service router is a high-performance carrier-grade router. It serves as the perfect validator because it requires the enhanced platform awareness, essential for a 5G UPF or vRAN. Specifically to support fast packet processing, it needs many of the EPA features, such as SR-IOV for the line rate throughput, CPU pinning for deterministic latency, and HugePages support for efficient memory access. Our demo setup connects two of these instances via the IPsec tunnel. On the edge side, the virtual cell site router aggregates traffic from the 5G distributed units co-located on the same cluster and acts as the IPsec tunnel initiator, encrypting traffic before it leaves the cell site. On the core side, the virtual security gateway acts as a centralized tunnel terminator. It receives and decrypts traffic from the remote sites, forwarding it to the 5G centralized units and core. During the demo, we are going to inspect the EPA capabilities in OpenNebula, Kubernetes, and the 6-wind virtual router, and finally generate some traffic between the tunnel endpoints. We'll begin with OpenNebula command line, inspecting the virtual machine with ID 360, which hosts our service router. First, notice the CPU pinning. Under the CPU IDs, we can see the specific host CPU indexes explicitly allocated for this virtual machine. This VM has 20 GB allocated, and crucially, all of it is backed by the HugePages to optimize performance. Finally, we check the PCI pass-through. The VM description shows a dedicated PCI device identified by its host address and the PCI address used inside the VM. If we switch to the hypervisor host view, we can confirm that this physical device, one of 4 available on the host, is exclusively claimed by the virtual machine with the ID 360. We can also see the NUMA topology, ensuring that the CPUs are pinned. The 20 GB of 2 MB HugePages are also booked and in use by this virtual machine on NUMA node with ID 1. Note the name of the virtual machine with ID 360 that we are tracing through the software stack. Now let's move up to the platform layer. We identify the Kubernetes node that corresponds to our OpenNebula virtual machine. By describing the node, we can see how these hardware features are exposed to Kubernetes. Under the node capacity, we can see 8 pinned CPUs and the memory reserved as 2 MB HugePages. Additionally, observe the special custom resource listed here. This indicates that the host has one consumable virtual function available. This confirms that the SR-IOV interface we saw passed through the OpenNebula is now recognized and schedulable by Kubernetes. Moving to the network function layer, we inspect the container running the 6-wind virtual service router. The left one acts as our security gateway, and on the right side is the one that acts as the cell site router. Here we can verify that the network interface card is visible with the exact same PCI address and model we saw on the hypervisor. This proves that control of the hardware has been successfully delegated through the hypervisor, through Kubernetes, and directly into the container. To validate data path, we will now generate traffic across the IPsec tunnel between the cell router and our security gateway. Initially, the throughput monitor on the tunnel shows zero activity. We can note the baseline packet count is sitting at roughly 600 packets. I will now trigger the traffic generator from the cell site router. Immediately, we see the throughput on the security gateway spike, showing active input and output bandwidth in the logs. The data path is live and leveraging the EPA acceleration. As soon as we stop, traffic drops back to zero. A final check of the logs confirms that over 1,000 packets were transmitted, successfully validating our cloud-native network stack with enhanced platform awareness. This work has been made possible by funding of the next generation European platform for the data center Cloud Edge Continuum project, co-funded by the European Union's next generation EU instrument through the Recovery and Resilience Facility. Thank you for watching and see you in the next screencast.